Hello everyone, welcome to my channel. So I've started offering specialized one-on-one classes in physics, chemistry and math EE for both SL and HL. So for the rates, the standard rate is $35 per hour. If you book like 5 or more classes, it'll be 30, and if you book 10 or more, it'll be 25. So these courses will be tailored to your needs. So whatever you want to learn, we can discuss in these classes. Please don't hesitate to reach out to me. You can contact me at this given email, and yeah, to schedule your class. So with this, let's get started with this paper. Thank you. Hello, welcome back to my channel. So today we'll be solving paper 2 of time zone 3 of the May 2025 attempt. Let's get started with the first problem. So they have given us three different indicators: phenol red, bromocresol green, and phenolphthalein, right? So state a functional group other than phenyl group that these three indicators have in common. So let's look for the groups. You have like three benzene groups in phenol red, yeah. You have this sulfur group, yes, sulfur oxygen, some type of group, and you have an OH group. Next in bromocresol green, yeah, you have the same group as the first one, yes, but you have bromine groups and you also have OH group. Fine, and in the last one, you have OH and you have an ester group. Okay. Now, if you look closely, OH is common in all the three indicators. Yeah. So the functional group which is common in all of them is OH, which is like the name of the functional group is hydroxyl. Next, deduce the color absorbed by the following indicators in alkaline conditions. Okay, fine. We have to use section 15 and section 18. Okay, section 18, it will tell you what's the color in acid and alkaline. So we have to find it in alkaline condition. In phenol, for phenol red, and alkaline condition is red. For bromocresol green, here the alkaline condition is blue. Now, so we have to use the color wheel to identify which colors are absorbed. Okay, so yes. Now see, for the first one, for phenol red, the color is red. Yes. So if it's red, so green will be absorbed. I'll just remove these annotations from the previous paper. Yeah. So as it's as it's showing you red, so red is visible, so green will be absorbed. Okay. So for phenol red, the color green is absorbed. Okay. For bromocresol green, the color which is visible is blue. So the color which will be absorbed is the opposite to blue. So has to be orange. Yeah. Next, we have to determine the molecular and empirical formulas for phenolphthalein. Okay, this is phenolphthalein, the third one. Let's count the number of carbon atoms and hydrogen atoms, everything. So 1, 2, 3, 4, 5, 6 carbons in this phenyl ring, 6 more in this phenyl ring, 12, 6 more here. So 18 carbons in the benzene rings, right? Then this one is the 19th carbon, this one is the 20th carbon. Total, you have 20 carbon atoms in phenolphthalein, right? So the molecular formula starts with C20. Next, I'll count the number of hydrogen atoms. You have one, two, three, four. Four hydrogen atoms here. Five, six, seven, eight. Eight, then nine. Okay. 10, 11, 12, 13, 14. Okay. After that, I don't think there is any other hydrogen atom. So all of the bonds are filled up. So there are 14 hydrogen atoms in phenolphthalein, right? And if you look for oxygen, you have total of four oxygen atoms. One, two, three, four. Yeah. So C20H14O4, that's your molecular formula. So empirical formula will be C10H7O2. Next. Yeah, to state the bonds responsible for absorption X, Y, and Z in the infrared spectrum of phenolphthalein. Okay. So absorption X is above 3500. Yeah. Let's move on to section 20. Yeah. And I'll remove these annotations. So above, sorry. Yeah, it is above 3500. So above 3500, there are two possibilities. Either it's an alcohol or it's a primary amine. In phenolphthalein, you don't have NH. So this one has to be from the OH group. Okay, OH groups present in phenolphthalein. The first one would be OH. OH as in any of these groups, these two. Fine. Next one. Next one is like in between 1500 and 2000. Probably a C double bond though, but we'll just check once. Mm, Yeah, C double bond aldehyde ketone esters carboxylic acid is between 1700 and 1750, which is a pretty strong intensity, right? So this one, the intensity is pretty strong, yeah, and it's around in the 1700 mark. So of course, this is the C double bond dip. And lastly, Z. Z is around 1200, somewhere around 1200, right? So if we check here, um, around 1200, yeah, we have the C single bond. Okay, so yeah, so these three absorption bands occurs because of these three groups. Next, we have to state the equation of phenol when it's acting as an acid. So we have phenol. This is water. It's would act as a weak acid, so reversible sign. O minus, right? Also equals, and then H3O plus. Right, so phenol loses an H plus, so it acts as an acid. Explain how the indicator H indicator, that is a weak acid, shows changes in pH during using an equation. So equation would be it's a weak acid, right? So this will combine with H2O, will form IND minus ion, H3O plus ion. So if this HIND has to be an indicator, the first and foremost condition is HIND and IND minus should have different colors, right? So right. Now, basically, using the properties of equilibrium, we can predict what, which color is expected in what condition, right? So, if acid is added, what happens is H3O plus concentration increases. Yes. If H3O plus concentration increases by La-Chatelier's principle, equilibrium will shift to the left, right? If it shifts to the left, your HIND concentration will increase. As a result, we will see the color of HIND. Okay. Now, if an alkali is added, then guess what? The OH minus will react with this H3O plus to produce water. Yeah. So H3O plus concentration decreases. Yeah. And the equilibrium will try to restore this H3O plus concentration by shifting to the right. And if the equilibrium shifts to the right, you will have more IND minus ions, and as a result, you will see the color of this IND minus. That is how a weak acid acts as a indicator, right? Next, models are useful for explaining characteristics and predicting outcomes. State and explain two properties of a liquid using the kinetic molecular theory model. Okay, this is pretty easy. So first, liquids are not compressible, they are incompressible. And if something is incompressible, they have a fixed volume. Right? This is because the particles in a liquid are close mm, together, yeah, and strongly attracted to each other. The other property is that liquids can flow, and they do not have a fixed shape because their particles are free to move. Done. And I think that's it with question 2. Move on to the third one, ammonia, right? So ammonia reacts with hydrogen to form, like nitrogen reacts with hydrogen to form ammonia, right? To define the equilibrium concentration, we know the moles of N2H2 and NH3 at equilibrium. So as we know the moles, you have to find the concentration. Concentration of N2 would be moles over volume, 0.545 mole per dm cubed. Moles of H2, I mean concentration of H2 would be 40 divided by 55, 0.727 mole per dm cubed. And moles of ammonia, NH3, this will be 6.17 divided by 55, which is 0.112 mole per dm cubed. So you have the concentration, so equilibrium constant would be NH3 whole squared divided by N2 times H2 concentration whole cubed. Now we'll just plug in the values and simplify. So 0.112 whole squared divided by 0.545 times 0.727 whole cubed. If you plug everything in a calculator, you will get 0.0599, which is your equilibrium constant. Next, the volume of reaction container of a mixture at equilibrium is suddenly decreased. Sketch the curve of concentration of nitrogen versus time until new equilibrium has been established at constant temperature. So this is where you'll have new equilibriums. I'll just draw a line. Ah. mm, Yeah. So when we are decreasing the volume of a container, what happens is initially concentrations will jump. Concentrations for ammonia, nitrogen, hydrogen, everything will jump because your moles remains the same but volume decreases. Okay. So firstly, the concentration of N2 will jump to some higher value. Okay. Then what happens is as your volume has decreased, okay, I'll just write it here. Okay. You can say pressure would increase. So equilibrium tries to decrease this pressure by shifting to the side with less moles of gas. Shifts to side. Right. So if you look here, you have less moles of gas on the right side. You have 2 moles of gas on the right side and 4 moles of gas on the left side. Yeah. So equilibrium will shift to the right. If it shifts to the right, what happens is concentration of N2 would decrease. Okay. But this concentration has to be higher than your initial concentration. So maybe we can draw it like this. Mm, So after this point has to be constant, sorry. Does it look good? Yeah. Okay, so this is the graph of concentration of nitrogen with time. To calculate delta G for the reaction at 450 degrees Celsius. We know Kc, so we can use this formula. Delta G equals minus RT ln K, right? So R is 8.314. Temperature has to be converted to Kelvin, so 450 plus 273, right? Ln, the value of K was 0.0599. If we just simplify, you will get minus 16921 joules per mole. Divided by 1000, you'll get minus 16.9 kilojoules per mole. Next, we have to outline how ammonia acts as a Lewis base when it forms the complex ion CuNH3 whole 4 H2O whole 2 2 plus. Yeah, forms a coordinate covalent bond with the central metal copper, right? Or with copper 2 plus, right? In a coordinate covalent bond, both the electrons will come from nitrogen, right? So we can say ammonia donates electrons to the Cu2 plus ion. That's why it acts as a Lewis base. Okay. So hence acts as a Lewis base. Done. The next question, we have to find the pH of 0.35 mole per dm cube solution of ammonia. The pKb value is given, right? So then set up the reaction NH3 plus H2O gives you NH4 plus OH minus, right? You need an ice table for these problems. So it's 0.35 initially, 0, 0. So I'll assume C concentration of NH3 got reacted, while C concentration of NH4 plus and C concentration of OH minus got produced. At equilibrium, these are your respective concentrations, right? So you know the value of pKb. So Kb is 10 to the power minus 4.75, which is 1.78 times 10 to the power minus 5. Okay. Now Kb would be NH4 plus ion concentration times OH minus concentration divided by NH3 concentration. Yeah. So Kb and everything else, we will get this. So it's C squared divided by 0.35 minus C. Now we have to make an assumption. Our assumption is C would be much, much, much smaller than 0.35 because ammonia is a weak base. Correct. So hardly any of it will dissociate basically. So 0.35 minus C can be approximated to 0.35. Fine. So 1.78 times 10 to the power minus 5 equals C squared by 0.35. From here, like we can directly find the value of C using a calculator, which is 0.00249. Yeah. C is basically your OH minus ion concentration. From here, if you find the pOH minus log base 10, the OH minus ion concentration, you will get 2.6. pH will be 14 minus pOH. So 14 minus 2.6, finally you get the pH as 11.4. That would be the final answer of this part 2. Yeah. Moving to the next question. Halogenoalkanes are used as refrigerants and solvents. You have to write the IUPAC name of this given halogenoalkane, right? So first I'll draw the structure. Now we have to first identify the longest chain. So this is the longest chain. Yeah. This longest chain has 4 carbon atoms. So your word root would be bute. All in between the carbon atoms, you have also a single bond. So butane. Right. Now about the prefix, we have to figure out the numbering. Okay. So if you number it in this way, your substituents occur at 2, 3, 3. Yeah. And if you take the sum, as all of them are substituents, not functional group, you can take the lowest sum rule. If you add everything, you get eat. And if you number it from the other side, 1, 2, 3, 4, yeah, your substituents will occur at 2, 2, 3. Take the sum, it gives you 7. So obviously the one in pink has a lower sum, so we'll go with the numbering in pink. Okay, the numbering on top has been rejected. So you have, so how do I write the name? You have two methyl groups at position 2, and you have a bromo group at 3. So we'll write it alphabetically. Bromo comes first, methyl comes later, right? So it's 2 bromo, I mean, sorry, 3 bromo, 2 comma 2 dimethyl butane. This is the entire name. Yeah. Next, you have to draw optical isomers of substance X. For substance X, this is your chiral carbon because it is connected to a hydrogen, right? If I just open up this bond, you'll see it is connected to a hydrogen, it is connected to a CH3, it is connected to this group, and it is connected to bromine. 4 different groups, right? So this is your chiral carbon. Okay. Now we draw this. Let's fix this bigger group on top. Yeah. You can fix CH3 here. And then first you can draw Br on your dash and hydrogen on your wedge. Now for the other isomer, you just have to take a mirror image, right? So this thing remains on top, there is no change, right? CH3 will come on this side, Br will go this side, and hydrogen will be here. So these are the two optical isomers of substance X. Next, we have to find the percentage of mass of hydrogen in substance X, just 4 significant figures. So I'll quickly find the molecular formula. It is 1, 2, 3, 4, 5, 6. C6, and the number of hydrogen atoms would be 3, 4, 4, 6 are 10, 3 are 13. C10, S13, Br. This is your molecular formula, right? So percentage mass of hydrogen. We have 13 hydrogen atoms, right? So numerator will be 13 times 1.01. 1.01 is the molar mass of hydrogen directly from the periodic table. Okay. They have asked you to use section 7, so you have to use the exact molar masses. Then you have to just divide it with the molar mass of the molecule. So 6 times carbon is 12.01, hydrogen is 13 times 1.01, and bromine is 79.90. Okay, and then multiply it with 100 to convert it to a percentage. Right, when you simplify this, you'll get 7.953%, and it says 4 significant figures, so you have to be careful. You need 3 places of decimal. Now, reaction between substance X and sodium hydroxide depends upon their concentrations, right? On their concentration. So, the concentration of the substance and concentration of sodium hydroxide. If a reaction, if any of these substitution reactions depend upon the concentration of both the nucleophile and the substrate, then it's an SN2 reaction. In SN1 reaction, only the concentration of the organic compound matters, right? But in SN2, both matters. So from just this statement, I know that it has to be an SN2 reaction. Yeah. So we have to explain the mechanism using curly arrows to represent the movement of electron pairs. Okay, fine. I don't think we need a 3D structure here. So, right. Now, in questions like this, remember in SN2 mechanism, there is always a backside attack. Nucleophile will attack from the opposite side of bromine, right? So, this electron pair will attack this carbon and bromine will get this electron pair, right? So first they will form this intermediate. So we'll just draw dotted lines here. There will be a negative charge, right? And then finally, you will have Br minus. This is the entire S into mechanism. Next, why CH3, CHI, CH whole thrice reacts faster than the bromine counterpart? Okay, now why does this iodoalkene reacts faster than a bromoalkene? So reason is simple because iodine has a much bigger atomic radii. If it has a bigger atomic radii, what happens is the atomic overlaps to form the covalent bonds are not that precise. Okay, so the overlap percentage is less. The bonds formed would be weaker. You can also think like this, that the covalent bond will be formed by sharing of electrons from iodine's valence electrons and carbon's valence electrons, right? Now, iodine's valence electron is placed at a much bigger distance as compared to bromine's valence electron. Yeah, because iodine is bigger in size. As a result, the nucleus of iodine won't be able to attract the shared pair towards itself strongly. As a result, the bond will be weak. Okay, so write the answer like this. This is because iodine has a much bigger atomic radii compared to Br. So the Ci bond is weaker than Cbr bond. Hence, it reacts faster. Done. Next, we have to differentiate between homolytic and heterolytic fission. In homolytic fission, your bond breaks equally, and both the atoms containing the covalent bond will receive one electron each. Receive one electron each. Yeah. For heterolytic fission, the bond breaks unequally, and one atom would receive both the bonding electrons. Say one of the atoms. Done. Next, we have to draw a structural isomer of molecule X. Um, Molecule X is our initial molecule, right? So we can just change the position of one CH3 group or change the position of bromine. Yeah. So 6 carbon atoms, 4. We can draw it like this, 5, 6, and then you can place the bromine here. 9, 12, 13. Yeah. Now moving on to the next question, ethyne, C2H2. Is a useful raw material in the synthesis of organic compounds. But to calculate the standard enthalpy change in kilojoules of complete hydrogenation of ethene to produce ethane, we have to use section 14 of the data booklet. So section 14 is probably there's the enthalpy of combustion. Okay, so for enthalpy of combustion, it is summation of, like the enthalpy of the reaction will be enthalpy of combustion of reactants minus sum of enthalpy of combustion of products. Okay, reactions is ethyne and hydrogen. Okay, so for ethyne, I have marked it here minus 1301. Then you have 2 hydrogen. For hydrogen, it is minus 286, the first one. Okay, and for products, C2H6, which is ethane, correct? For ethane gas is minus 1561. Yeah. If you simplify this, you'll get negative 312 kilojoules per mole, which is the answer to A1. We have to calculate the temperature at which this reaction is no longer spontaneous, right? So the reaction becomes no longer spontaneous when delta G becomes 0 or when delta G is equal to 0, right? So delta G equals delta H minus T delta S, correct? So delta H, we have found it as negative 312 times 10 cubed. Temperature is what we need to find. Delta S is negative 233. You have to equate this to 0 and then find the value of T. So 233T would be 312 times 10 cubed. From here, temperature will be 1339.05, which you can round it to 1340 kelvins, right? And that's your answer. So any temperature above 1340 would make your reaction non-spontaneous. Fine. The next one, you have 140 centimeter cube of ethane which reacted with 160 centimeter cube of hydrogen at this temperature and pressure, and ethane is the only product. Maximum possible volume of ethane. So the reaction should be like, this given reaction. So C2H2 gas plus twice H2 gas gives you C2H6 gas. Fine. So C2H2 is ethane, C2H6 is ethane. Okay. Now first you have to find the limiting reactant. Now as everything is a gas, we can directly use volumes in this question. We don't have to convert anything to moles as such, right? So we can take the volume ratio. We can take V, volume by stoichiometric coefficient for C2H2, which is 140 divided by 1. Volume of C2H2 is 140, stoichiometric coefficient is 1. And volume by stoichiometric coefficient for hydrogen would be 160. Volume of hydrogen is 160 divided by 2. The stoichiometric coefficient is 2, 80. The one which is smaller is a limiting reactant, so H2 is a limiting reactant. Now we'll find the volume of ethane. So volume of C2H6 by volume of H2. This would be 1 over 2, right? So volume of C2H6 divided by volume of H2 would be 160, 1 over 2. So volume of C2H6 finally becomes 160 by 2, which is 80 centimeter cube. The maximum 80 centimeter cube of ethane will be formed. Next, we have to draw the Lewis formula of C2H2, that is ethane. Ethane is C triple bond C, and then we'll place one hydrogen at the ends. You have to state the hybridization of carbon atom in C2H2. So if you take any one carbon atom, around this has one sigma, a single bond is one sigma bond, right? And if you look at the triple bond, it has one sigma bond and two pi bonds. I need only the number of sigma bonds and the lone pairs. You don't have any lone pair on this carbon, so no need to worry about it. So there are a total of two sigma bonds, yeah. Two sigma bond means you will choose the first two orbitals. First is 1s, and then the second one would be p. So hybridization is sp. Done. That's it about C2. Okay, and then we move on to the next question. We have a lithium-ion battery consisting of lithium ions on lithium graphite LiC6 and lithium cobalt oxide LiCoO2. Okay, fine. The lithium ions are produced at the anode from lithium atoms embedded in graphite. We have to state a half equation for reaction occurring at anode during discharge, right? So anode, basically lithium gets oxidized to Li plus. Lithium, which is embedded in graphite, LiC6, so this becomes C6 plus Li, right? So Li solid will become Li plus, okay? Li plus, is it an aqueous solution? It's not given, so all right, let's not provide any states here. We can just write Li gives you Li plus electrons. That is the half reaction for the half equation for the reaction occurring at anode, right? Comment the sign and value of a reduction potential of lithium that makes it suitable to use in the battery using section 19. Section 19 probably gives you the E0 values. Yeah. So if you check, lithium is exactly on the top of the table. right? So Li plus has the highest negative E naught value. That means the reverse reaction is highly spontaneous. Li can easily oxidize to form Li plus, so it is one of the best reducing agents. Yeah, so and write the answer like this: has the highest negative E naught value, which means Li is one of the strongest reducing agents. And hence can be used in a battery. The next part, the lithium-ion battery is rechargeable. Annotate the diagram below to show the direction of electron flow when battery is recharging. Okay, so here what was happening is electrons were generated at the anode, right, and the electrons were getting transferred to the cathode, right? In the reverse reaction, right, when you're recharging, the electron flow will exactly be the opposite. It will come out of the cathode, right, and it will reach the anode. Done. Suggest why solar panels are often connected with lithium-ion batteries. Basically, the electricity generated in the solar panels are used to recharge these lithium-ion batteries, right? So can be used to recharge lithium-ion batteries. Okay, done. Next, a charge of 1000 coulombs passes through a lithium-ion battery during discharge. You determine the number of lithium ions released at anode. Okay, first we have to find the moles of electrons which passed. So to convert charge to moles, you divide it with 96500. Yeah. So 1000 divided by 96500, this gives you the moles of electrons, which is 0.0104. Now, this was the reaction. Lithium becomes Li plus electrons during discharge. So you have to find the moles of Li. So Li plus and electrons, they are in 1:1 ratio, right? So moles of Li plus will be equal to moles of electron, which is 0.0104, right? Now, if you want to find the number of Li plus ions, this will be moles 0.0104 times 6.02 times 10 to the power of 23, which gives you 6.24 times 10 to the power of 21, which is the answer to this part D. Now, question 7, we have nylon 66, which is a polyamide used in many things. Okay, fine. So we have to find the structures of two monomers. So here, just find the two identical functional groups. So here's C double bond O. And if you check here, or like, the adjacent part, this is one monomer, yeah, and this will form the other monomer. The first monomer, instead of NH, just make it NH2, right? So NH2, CH2 whole 6, NH2, right? The other one will be a carboxylic acid, so COOH, CH2 whole 4, and then COOH again. Done. The strength of nylon 6s is due to hydrogen bonding between the polymer chain. We have to annotate these hydrogen bonds. So hydrogen bonds will be in between the oxygen and the hydrogens, like this. Oxygen and this hydrogen, which is connected to the nitrogen atom, right? Now we have to outline how a hydrogen bond is formed. Okay. So you can just write it down. Hydrogen bond is formed when a hydrogen atom is covalently bonded to a very electronegative and small atom like fluorine, oxygen, or nitrogen. Okay. This hydrogen containing the partial positive charge will be attracted to a lone pair on, again, fluorine, oxygen, or nitrogen of a neighboring molecule to form the hydrogen bond. That's all about this part 2. Next, we have to discuss the following in terms of bonding and intermolecular forces. The silicon's boiling point is very high, while polyethene's melting point is low. So why does silicon has such a high melting point? Because silicon has a property of catenation. So if you look at a silicon atom, it is covalently bonded to each other. Each silicon atom is covalently bonded. Okay? Just like carbon, silicon also shows this exact same property. Yeah. So silicon shows catenation. Silicon atoms are bonded together by single covalent bonds. Okay. But polyethene is a non-polar molecule, right? Hmm. So the chains of polyethene are held together by weak London dispersion forces. The chains are okay, as polyethene is non-polar. Now, as covalent bonds are much stronger than London forces, hence silicon has a higher melting point. To polyethene. Done. That's all about this part C. Now moving to question 8. Mechanism of an exothermic reaction is given. You have to state the products. Yeah. So if you just add up these reactions, you'll get the products. So D will get cancelled out on both sides. Yeah. And finally, you'll get A plus 2B gives you C plus E. So C and E are your products. Okay. Fine. Next, we have to sketch the energy profile for this reaction, indicating labels, products, transition states, and intermediate. It's an exothermic reaction, so heat is released. So reactants have higher energy compared to products. This will be products. Now here it's a two-step mechanism, right? So it will look like this. Yeah, the second step is the slower step. So the second step will have greater activation energy. Okay. So I can start labeling things. This is your enthalpy, delta H. This is EA1. This is EA2. Transition states are formed at the top, right? So this is a transition state. This is a transition state. At the middle, this one would be your intermediate. We have labeled reactant products, transition states, intermediate, everything. So this should be our answer. Next, we have to reduce the rate equation for this reaction. So we take the slow step, okay? The rate would be K times D times P, right? Now this T, which is an intermediate, is formed by A and B. So you can replace D with the common product of A and B. This gets you K times A times B squared, which is your answer to part 3. Now for this next question, we have to explain how increasing temperature increases the rate of reaction using collision theory. So basically, when we increase temperature, that the main change is the molecules will have more energy, right? So if the energy of molecule increases, what happens is you have more molecules which have energy greater than the activation energy, right? When molecules have more energy, they'll also have more kinetic energy, right? So their speeds will also increase. So as they move faster, what happens is the number of collisions will increase per unit time. Now we have two effects. One, you have more molecules with energy greater than the activation energy, plus you have more number of collisions. So what happens is directly would lead to a greater number of effective collision. As a result, your rate of the reaction will increase. Yeah. So write it like this. On increasing temperature, molecules gain energy. And now more molecules greater than the activation energy. As the kinetic energy of molecules increase, what happens is molecules start moving faster, resulting in an increased number of collisions per unit time. Now, both these effects tend to increase the number of effective collisions per unit time, increasing the reaction rate. Now, moving to the next question. Ethanol is a biofuel, right? That is made from glucose. Glucose is formed by biological fixation of carbon through photosynthesis. The equation of photosynthesis, which is the reaction of CO2 with water to form glucose and oxygen. To balance it, I have to put a 6 here, right? And there is 6 extra oxygen, so 6 here. I mean, 12 extra oxygen atoms, so 6 in front of O2. Right? So we need to list two advantages of ethanol as a fuel instead of gasoline. Yes. So first is ethanol is a renewable resource, right? So we can keep on producing ethanol. And secondly, ethanol does not contain sulfur, right? So ethanol will not cause like acid rain, but if you burn gasoline, it will produce SO2 gas, which will in turn from cause acid rain. Yeah. So contains sulfur, which is responsible for acid rain. Next, You have to calculate the enthalpy change of the combustion reaction of ethanol using section 12 of the data booklet. All right, let me quickly load the data booklet. You have to move on to section 12. Yeah, section 12 is the bond enthalpy. So, okay, for bond enthalpies, you have to draw the structures of the reactants and products. So, bonds broken would be 5 times CH, 5 CH bonds are broken, 1 CC bond is broken, 1 CO bond is broken, 1 OH bond is broken, and then 3 O double bond O would be broken. These are the bonds broken. Okay. And if you list the bonds formed, it would be 4 C double bond O and then 6 OH. Now delta H would be summation of bonds broken minus summation of bonds formed. Now we need to fetch these values from the data booklet. So for summation of bonds broken, you have 5 times CH. CH would be here 414. 1 times C single bond C. C single bond C is just below 346. 1 times C single bond O is 358. 1 times OH. OH would be here 463. And then you'll have 3 times O double bond O, which multiple bonds you can find here 498. Okay. The summation of bonds broken. And then we have to subtract the bonds formed. C double bond O is 804. So 4 times 804 plus 6 times OH. OH we have already found here, it's 463. Fine, if we plug it in a calculator, we'll get minus 1263 kilojoules per mole, which is the enthalpy of combustion of this reaction. Done. Next, we have to calculate the increase in temperature in a sample of 500 centimeter cube of water heated by the combustion of 5 grams of ethanol. Okay. First, we'll find the moles of ethanol. It will be 4 divided by the molar mass of ethanol. Ethanol is C2H5OH, right? So 30 and 16, 46. So 0.08969. Sorry, 0.08696. Yeah, that is the moles of ethanol. Now heat released, this Q is the heat released, okay? This will be moles times the enthalpy of combustion. So 0.08696 moles of ethanol times the enthalpy of combustion you found in the previous part. Okay. No, wait. They are asking us to use section 2 and section 14 here specifically. Okay, section 14 gives you the enthalpy of combustion. All right. So for ethanol, enthalpy of combustion is minus 1367. Okay, 1367 times, okay, let's just keep it like this. Yeah. So if you multiply them, you'll get 118.87 kilojoules. So you might think why I like rejected the negative sign on delta H, because I have already assumed this is the heat released. Okay, negative delta H means heat has been released. So if I just write it's like it is the heat release, then I'm like already considering the negative in the statement itself. So 118.87 kilojoules of heat was released. Now this heat will be used to heat up the water. So 118.87 times 10 cubed equals the 500 centimeter cube of water, right? Water has a density of 1 gram per centimeter cube. Okay, that means 1 centimeter cube of water weighs 1 gram. So 500 centimeter cube of water will weigh 500 grams. Okay, the mass of water is 500, C is 4.18, yeah, and you have delta T. From here, if you find delta T, you'll get delta T as 56.9 degrees Celsius. which is the answer. Now the last part, explain the strength with atomic radii of atoms in an ethanol molecule. Okay, now hydrogen will obviously be the smallest because hydrogen belongs to group 1. It has one shell of electrons, while oxygen and carbon belongs to group 2. So it has two shells, which has to be bigger than hydrogen, right? So hydrogen belongs to group 1, so has one shell, while oxygen and carbon, I'm sorry, I'll say period 1. Oxygen and carbon belongs to period 2, hence has two shells. So therefore, hydrogen is the smallest. Now we are done with hydrogen. We have explained why hydrogen is the smallest. Now we have to compare between oxygen and carbon. Okay. So as oxygen, so oxygen has a higher atomic number compared to carbon, right? Carbon's atomic number is 6, oxygen is 8. So oxygen has more protons as compared to carbons. Yep. So electrons will be attracted more strongly by oxygen. As a result, has a smaller atomic radii compared to carbon. Okay, that's it. Now moving on to the last question. Yes. You have to write the electronic configuration of sulfur first. Sulfur has an atomic number of 16, right? So 1s2, 2s2, 2p6, 10 electrons done, 3s2, 3p4. All done. This is the electronic configuration of sulfur. Next, we have to draw the Lewis structure of SO2. We have to find the total number of valence electrons first. The valence electrons will be sulfur has 6 valence electrons, oxygen also has 6 valence electrons. A total of 18 valence electrons, and if you want to find the number of electron pairs, you will do total valence electrons divided by 2, that is 9. We are starting with 9 electron pairs in this case. Yeah. So sulfur, oxygen, oxygen. So out of this 9, you'll use up 2 electrons to first connect the sulfur with the oxygen atoms. Okay. Then you will complete the octet of every oxygen atom. You see 6 electron pairs are gone. Left with 1, you have to place it on sulfur. Still, you'll see sulfur's octet is not complete. Okay, so what you can do from here is you can remove one of the lone pairs on an oxygen and construct a double bond between the oxygen and sulfur. Okay, so this is one Lewis structure of sulfur. Yeah. In this Lewis structure, you'll have a positive charge on the sulfur and negative charge on this oxygen. Because sulfur and oxygen belong to the same group, the expected number of electrons is 2, but sulfur has 1 electron, less than 2, that's why it has a positive charge. Oxygen has 3 electron pairs, greater than 2, so that's why it has a negative charge. Now, another possible structure would be the expanded octet of sulfur. In that expanded octet, what happens is this oxygen will also produce, form a double bond with this sulfur. Now, both the oxygens will have 2 electron pairs each, so there is no charge on oxygen. And as sulfur forms an expanded octet, it will also not have any charge. This is the more stable Lewis formula. Done. Next, we have to reduce the electron domain geometry and molecular geometry of SO2. So you have 3 electron pairs around sulfur. Okay. Basically, you have 1 lone pair and 2 bond pairs, right? If you have 3 electron pairs, the electron geometry will always be trigonal planar. For the molecular geometry, if you have 2 bond pairs and 1 lone pair, basically it forms a bent shape like this, basically. Okay. So molecular geometry would be, we'll reduce it by using 2 bond pairs and one lone pair. Molecular geometry will become bent. Done. Next, we have to explain the polarity of SO2. In SO2, sulfur molecule has a lone pair, right? If you have a lone pair on the central atom, the molecule will be polar. So I know it initially that SO2 will be a polar molecule. You just have to write the reasoning behind it. Okay. So now we can write it like this. This is because the molecule is unsymmetric and the dipole moment of sulfur lone pair is much bigger than the dipole moments of S double bond O. Hence, the dipoles do not cancel out. As a result, SO2 is polar. Now the last question in this paper. Sulfur dioxide reacts with acid rainwater and oxygen to form sulfuric acid. Write an equation including the state symbols SO2 gas plus H2O liquid plus O2 gas. These are your reactants. It gives you H2SO4. So we have 2 to the 4, 5 oxygen. So if I put a 2 in front of H2SO4, then I have to put 2 in front of H2O. I have to put 2 in front of SO2. I think this balances out the reaction. 4 2s are 6 2s are 8. Yes. 8 oxygen on the left side, 8 on the right side. Yes, this is the reaction between SO2, rainwater, and oxygen to form H2SO4. And that's all for this paper. Thank you so much for watching this video. And I'll see you all in the next one. Bye-bye.